Hey guys, we're going to do a quick crash course on lab math for your lecture exam that's coming up next week. Just note this is not going to be all inclusive. I'm not talking about a lot of the stuff that comes up in your laboratory portion of your class. I'm really just talking about the stuff that comes up in the lecture portion of your class. But we're holding hands. We're going to get through this together. I love math. I don't expect you to come out of this loving math. I just hope to make this a little bit less painful for you. So here's our laboratory math crash course. We're going to be talking mainly about your AG ratio, your AG gap, and your osmolality. I'm going to mention at the end a couple of other formulas that you should be aware of. You won't necessarily have to know how to do the calculations, but you should at least be able to look at them and see them and know what they are. So let's go ahead and get started. First and foremost, what is our AG ratio? Our AG ratio is essentially a comparison of albumin to all other proteins. So in this case, it is albumin to all other proteins, aka globulins. Our reference interval for this is 1.2 to 2.2. So real quick, because this is a ratio, ratios are always going to be something over something. So in this case, it's albumin over globulins, and we measure that in grams per deciliter. Grams per deciliter. When we do this, these are going to cancel out. Ratios do not have units of measurement. And for those of you who've taken advanced math courses, I'm sorry. I really do like to dig into the theory of why math works the way that it does, because I do think that it helps a lot of people. So a lot of this is going to feel really simple, but I think that it's important sometimes to cover the basics so you can understand how the basics integrate into the complicated, if that makes sense. So real quick, we need to go over how ratios work. So if you remember from elementary school math, you have a number over a number because you have a fraction. If I have an increase in the top number and the bottom number doesn't change, or I have a big increase in the top number and a small increase in the bottom number, or I have an increase and a decrease, or I have it stay normal here and it decreases down here, all of these are going to result in an elevated ratio. Okay? If I have this go up, this go up, this is normal, this is normal, this go down, this go down, this is going to be a normal ratio. And then if I were to take all of these and flip them, so I have a decrease here, normal here, decrease, 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 increase, or I have it be normal here, and I increase this, all of these are going to result in a decreased ratio. Why is this important? You don't have to memorize this. This is just digging into theory. In our context here, we're looking at albumin over our globulins. So if I have a decrease in albumin and my globulins, relatively speaking, stay normal, then I'm looking at potentially having a decreased ratio versus if I have, a double increase in what my expected albumin is and a, slight increase in my general globulins, that's going to be an increased ratio probably. It doesn't always work out that way math-wise, but we can kind of guess that that's the direction the ratio will end up going when we get there. So we're going to walk through the math and how the math works. And I unfortunately think that the best way of doing that is to go through a series of case studies. I'm holding your hand. We're walking through it together. I will pause to explain any potential medical terminology that comes up, but I do think it's important to understand how the math works, why it works, and the context in which it works, because I think that that helps you understand the clinical implications of what's going on. Okay? So our formula is up in the upper right-hand corner. It's AG ratio albumin over total protein minus albumin. Total protein minus albumin is how we calculate our globulins. Because what are globulins? Globulins, oh my goodness, go away. That was weird. Yeah. Our globulins are our total protein minus our albumin, aka not albumin. Okay. If I have an elevated albumin, we'll get into that in a second. So let's go ahead and read through our case study. A patient presents to the emergency department complaining of NVD. NVD is nausea, vomiting, and diarrhea. This is a medical term that we use to very quickly say that they have all three things going on. NVD. It's important to know that you have vomiting and diarrhea in certain cases because vomiting results in a loss of water and chloride. Diarrhea results in a loss of water and chloride and everything basically. We need to know that we are losing stuff out both ends, essentially. So when you have nausea, vomiting, diarrhea, especially when it lasts for, like this patient, 3 days, that's 3 days of consistent significant water loss. That can cause your body to do all sorts of weird things. So that's why it's relevant that they have both vomiting and diarrhea. Okay. Patient reports several bouts of severe, again, watery, important that it's watery, diarrhea over the previous 3 days. Physician orders a BMP, which is a basic metabolic panel, and an electrolyte panel. Results indicate that the patient has an albumin of 6.8 grams per deciliter and a total protein of 9.3 grams per deciliter. So we're just going to go ahead and circle those so that I can quickly see them. 6.8 and 9.3. What is the patient's AG ratio and what is the interpretation of the value? So we're going to pull our formula down. Our ratio equals albumin over our total protein minus our albumin, aka our globulins. So our albumin value is 6.8 grams per deciliter over 9.3 minus 6.8 grams per deciliter, which is going to simplify down to 6.8 grams per deciliter over 9.3 minus 6.8, 2.5. So we have 6.8 grams per deciliter of albumin and 2.5 grams per deciliter of globulins. Right, that is 2.5, right? 6, 7, 8, 8.8. Yeah, 9.38. Okay. 6.8 albumin, 2.5 globulin, which is going to roughly simplify down into, and I do need a calculator for this one. Typed it in wrong. 2.72. Now, our reference interval is 1.2 to 2.2. 2.72 is way over there, which means that this is an elevated AG ratio. So, our answer is 2.72, and our interpretation is elevated AG ratio. Now, AG ratio in this instance is elevated because the patient has been losing a lot of water. So when the patient loses a lot of water and there is no like requisite kidney damage, what ends up happening is the amount of solute that is present in the blood concentrates down. So the end result is that because there is significantly less water to dilute out all of the proteins, everything kind of gets more. Everything kind of elevates. In this instance, albumin is going to be larger than the total protein because your total protein, your globulins, also consist of something called like immunoglobulins, which are antibodies. And you can lose antibodies through your urine. Very small. So because you're like, vomiting stuff, because you're pooping a lot and you're losing a lot of water through your feces, you could also potentially be losing antibodies that way or other like waste proteins that your body is trying to get rid of. And so because you're holding on to albumin, but you're not holding on to the rest of your proteins as much, you end up with a situation of either this and this with, or this and this, or this and this, or this and this. It's magic. Anyway, the point is, in this instance, patient lost too much water, which is what caused their stuff to get elevated. So let's do this again. Patient reports to the emergency department complaining of aching bones. Reports that this has been going on for several months, but tonight they felt dizzy after physical exertion. These are clues to a specific disorder that the patient may be experiencing, which we'll get into after we do the math, and I'll walk you through what you would do next based on this information. The physician orders a CMP, so a comprehensive metabolic panel, which is basically the fancy version of our metabolic panels that we do in chemistry, as opposed to the basic metabolic panel, which is basic. They order a CMP and several hematology studies. The CMP indicates the patient has an albumin of 3.6 and a TP of 8.9. What is the patient's AG ratio and what is the interpretation of this value? What reflex test should be ordered? So let's get into this first. Let's walk through our math. So our ratio equals albumin over TP minus albumin, which is going to equal, in this case, 3.6 over 8.9 minus 3.6. It's going to roughly be 3.6 over 5.3, which if you can look at that, you're already going to be able to tell because this number is so much smaller than this number. You're already going to be able to tell that this is going to be a low ratio. So that's going to equal roughly 0.64. So again, 1.2, 2.2. This is significantly lower than 1.2. So far, our answer is 0.64 is our ratio of albumin to globulins. Now, what is this result indicating? Well, because we have such a low ratio, the implication here is that, either you've got decreased albumin and increased other proteins, so increased globulins. You've got normal and double increase. You've got normal increased, stuff like that. In this instance, we can tell that our TP is elevated. And we can tell that our albumin is fine. That implies that because our albumin is fine and our TP is elevated, that implies that our globulins are also going to be elevated. Because if you have something that is abnormal and it's made up of something that is normal and something else, that implies that the issue has to be coming from the thing that is the something else, if that makes sense. Because of the fact that the globulins are abnormal, remember a second ago, I think I said it in this version, I may not have. One of the biggest things that makes up our globulins is something called immunoglobulins, which is basically antibodies. So if I have an elevated globulin amount in my body as opposed to elevated albumin, like my albumin's normal and I have high globulins, one of the first things that I need to make sure that is not wrong with the patient is their immunoglobulin level. I need to make sure that their distribution of immunoglobulins is good. Otherwise, I need to go out of my way to check that it's not immunoglobulins causing the issue, right? The test that we do to figure that out, which, hold on, interpretation would be low AG ratio. Sorry. Because I know that the issue is coming from my globulins, I need to make sure that it's not my immunoglobulins, because that can cause issues. If it is the immunoglobulins, that implies cancer, essentially, or at least like a dysplasia, a bone marrow dysplasia. So because the globulins are out, we need to investigate that. And the way that we investigate that would be SPEP, would be our reflex. I wouldn't even call this necessarily a reflex. It's just what follow-up tests should be ordered. We would do an SPEP because we need to figure out what's causing it. Now, this is something that y'all will go into later, but I do want you to be aware of it. Complaining of aching bones and feeling dizzy after physical exertion is an indicator of two specific symptoms of a disease that you will go into later. It's basically bone pain, aching bones, and anemia. And there are two other symptoms that we don't care about right now. These are indicative of a condition called multiple myeloma. So with our SPEP, what we expect to see on this, because we've got symptomology of multiple myeloma, would be an M spike, which I know y'all have been over SPEPs, so just make sure that you're correlating these things together. If you have an SPEP that's got an M spike, you would expect that if you looked at that same patient's AG ratio, their AG ratio in an M spike is probably going to be low. Does that make sense? Everything is related. And that's why I want to go through this in the context of like case studies, is because I want y'all to see that like if this patient has a low AG ratio and we we do a SPEP as a follow-up, and the SPEP comes back with an M spike, the M spike makes sense because that correlates to a low AG ratio, because an M spike is made up of, generally speaking, immunoglobulins. So that's when we have this, and it goes like way up, and then we have our other little stuff. The M spike is right there. Immunoglobulins are generally very small, so they're the first ones to drop off on your SPEP. And it makes this huge, huge, huge sharp point Immunoglobulins are globulins. The more globulins you have, the smaller your Ag ratio gets. People with an M spike have multiple myeloma. Multiple myeloma patients have the M spike. M spike correlates to low Ag ratio. Low Ag ratio, in turn, correlates to multiple myeloma. Everything is connected. Anyways, next, anion gap. Note, you will sometimes see this referred to as Ag. Always differentiate this from a G ratio, A over G. Anion gap and Ag ratio are not the same thing. Your anion gap is the difference between the positive and negative ions present in your blood. Your reference interval for this is 10 to 20 millimoles per liter. So let's go through this in the context of a case study again. I've got your formula up in the upper right-hand corner. We'll walk through. Did I go over? Yeah, I did. Oh, also, last thing I want to add to this, sorry. If we have an M spike on our SPAP, we would follow up with an IFE, the immunofixation electrophoresis. Sorry. Anyway, case study, anion gap. Changing course, fixing our brains on the new subject. Anion gap. A patient with known liver cirrhosis, so liver problem, generally considered damage. This patient is receiving routine maintenance chemistry testing. So just like generally speaking, BMP. If they have a known liver problem, they may be getting electrolytes thrown on that as well because they want to monitor to make sure there's no like kidney involvement as well, stuff like that. So like whatever their routine maintenance testing is, that's what they would be receiving. Using their electrolyte results, calculate their Ag. So we're just going to take our formula from up in the top corner, which is going to be our sum of our positives, and we're going to subtract the sum of our negatives. So in this case, that would be 136 plus 4.1 minus 99 plus 24. Real quick, we can verify that our sodium and our chloride are trending together. 135 to 145 is our normal. This is on the low end of normal. 98 to 107 for chloride. This is again on the low end of normal. This patient is okay, or at least these results are okay. This is good to go. So 136 plus 4.1 is 140.1 minus, what is that, 123. And this is where my brain is gonna not want to work. 140.1 minus 123. It's gonna be 17.1. So their Ag equals 17.1. Normal Ag is again 10 to 20. This is normal because 10, 20, 17.1. Yay, he's okay, at least in terms of his electrolytes. Okay, the anion gap is just basically, are you electrically balanced? That's the whole goal that we're trying to find here. Oh, I had bad notes. Okay. It's pretty easy. It's pretty straightforward. I don't think we need to go into it too much. I just think that the thing that confuses a lot of people is the physical formula itself. They look at this and they're like, that's really ugly. And I agree, it is ugly. Make it simpler. It's not a hard one. It's not a complicated one. You're going to be fine. It's really just a plug and chug. So, osmolality. Osmolality is a measure of how much stuff is in a fluid. That's it. That's literally all that it is. And I think that it freaks a lot of people out, especially because you start to get into like osmolality versus osmolarity. And that has to do with like whether or not you're measuring it per kilogram or per liter. That's literally the difference between osmolality and osmolarity. Uh, for right now, what we're working with, just know that osmolality is how much stuff is in a fluid. That's it. We have two ways of like really talking about osmolality. It would be your serum, so how much stuff is in the liquid part of your blood versus how much stuff is in the liquid of your urine. The liquid part of your urine, how much stuff is in your urine, how much solute is dissolved in your pee. Dissolved. It's midnight, sorry. How much stuff is dissolved in your urine. Depending on like the osmolality of your urine, if you have kidney damage and your urine osmolality is really increased, you're losing a lot of stuff through your urine that you should be reabsorbing. So this can happen in something like nephrotic syndrome, where you basically have just punched a bunch of holes in your kidney nephrons, and all of a sudden you're losing water, you're losing solute, you're losing everything, you're losing too much, and too much of that stuff is being found in the urine, hence why it's elevated. On the other hand, if your serum reference interval for osmolality is too high, it could be indicative of the fact that you're not excreting enough stuff through your urine. It could be you're dehydrated and your serum is concentrating down, et cetera, et cetera. There's a lot of things that can come into play and impact your serum versus your urine reference interval for osmolality. We'll get into it. But first, this is a beast of a formula that for some reason really does trip a lot of people up. And so the thing that I want to go into on this formula is what the formula means, because I do think that understanding what is going on here will help you figure out how to remember it for your own purposes. So, first and foremost, what is the 1.86 for? Why do we do the 1.86? Well, if you will notice, there is nothing on this formula that accounts for chloride. Where is chloride? Well, we don't include chloride here because we're making an assumption that chloride is present in an equal concentration to sodium. Unfortunately, like, it is literally just us being like, well, sodium and chloride are supposed to trend together. They're supposed to be similar, and this will get us roughly into the same like area if we just do the same math instead of including the calculations for both sodium and chloride. Both sodium and chloride are extracellular ions. Sodium is your extracellular cation, chloride is your extracellular anion. Because they are both extracellular, they are both outside of the cells, they are both easily available within the serum for us to test. Because they are hanging around in the serum, they are consistently going to be a big player in the actual osmolality of the serum because they're dissolved in the water that is the serum, right? Rather than including both the concentrations of sodium and chloride, what we do instead is multiply sodium by, and it's called something really fancy, and I cannot for the life of me remember what it is, but basically, 1.86 divided by 2 is 0.93. 0.93 is 1.86 is 2 times the effect that sodium has on osmolality. And this is where we start to get into like, it's like I think it's like coefficient of osmolality or something like that. It's basically like, how much of a difference does this thing make compared to regular water? But it's like, it's like a standardized number, if that makes sense. The only thing that you need to know here is that the 1.86 is present because it is how we compensate for chloride not being included in the formula. So we're basically just doubling the effect that sodium has on the osmolality because we're assuming that chloride has an equivalent effect on osmolality to the sodium. It's not 2 perfectly because sodium doesn't have exactly a number, like a number one effect. That being said, there are some versions of the formula you will see that use the number two because they like to make their lives easier instead of us who likes to make our lives actively harder. Some formulas you'll see they'll use two instead of 1.86. We use 1.86 because ASCP hates us. That's really what it boils down to. So this is how we compensate for chloride. Here is my favorite part of this whole thing. Are you ready for this? Why is glucose 18? Why is it that we're dividing the concentration of glucose by 18? Let's get into it. So, the important thing that you need to understand is that the concentration of glucose is measured, generally speaking, in our lab, in milligrams per deciliter. When we are calculating osmolality, we need this to be measured and reported in one of two ways. It needs to either be milliosmoles per kilogram or millimoles per liter. The math works out the same either way. I will be using millimoles per liter because I don't feel like bringing in kilograms into this. It doesn't matter. What matters, the math ends up working out the same either way. It just depends on what direction you take it. Is really what happens. Milliosmoles requires like bringing in a coefficient of everything, and I don't want to do that right now. So we're just going to stick with millimoles per liter. All that matters is that the math works out the same either way. So milligrams per deciliter. Well, if you remember from general chemistry, now I need to convert my milligrams to millimoles because I need to get it to that format. Which also, by the way, we measure these in millimoles per liter, which is why the sodium doesn't need to get converted in the same way that BUN and glucose do. So because this is already in the format that we need it to be in, we don't have to do the conversion, which is what this is. Anyway, I have my milligrams per deciliter. I need to convert milligrams to grams. So that's going to be my ratio of grams to milligrams. Now I need to convert grams to moles. So for glucose, the molecular weight of 1 mole of glucose is 180 grams per 1 mole. And now I need to convert moles to millimoles. So that would be 1 mole equals, is it 10,000 or no, it's 1,000. 1,000 millimoles. And then that would leave me with milligrams will cancel out, grams will cancel out, moles will cancel out. So I'm left with glucose, the amount, whatever the number ended up being, times 1,000, I'm running out of space, 1,000 millimoles over 180, because I've still got that left, times 1,000, and I've still got deciliters left. So I'm going to rewrite that so it's a little bit neater. So my glucose, I'm left with 1,000 millimoles over 180 times 1,000 deciliters. Now I still need to convert deciliters to the liters that we need to get in order to answer the overall question. So the way that I would do that is I would do 10 deciliters over 1 liter, and that's going to cancel out my deciliters, and that's going to leave me with 1,000 times 10 millimoles over 180 times 1,000 liters. Math-wise, the 1,000 and the 1,000 are going to cancel out, which leaves me with 10 millimoles of glucose per 180 liters. You can cancel out the ones. You're left with 1 millimole of glucose per 18 liters. So then all that we have to do math-wise in the formula at that point, this is our conversion factor. This is how you would convert that amount of glucose over into whatever format you need it to be in for your overall formula. At that point, you could just plug and chug. So it would be whatever your glucose concentration is times 1 over 18 millimoles per liter, which is how we get to concentration of glucose over 18. I know that that's crazy and really annoying, and it does take a minute to get through it. That's why the formula is the way that it is. So you could repeat all of this same math for BUN and get to the end result. Blood urea nitrogen in this context is N2. The atomic weight, or like I guess the molecular weight is how I should be saying it. Molecular weight for nitrogen is 14. If you have 2 of them, that would be 28, which you would follow all of this math again, except instead of 180, it would be 28 grams. And that's how you would eventually get down to the BUN, is the concentration of BUN divided by 2.8 is how you get there. I know that that's crazy. For some people, that's going to help you. Take what helps, leave what doesn't. Like, this is a TikTok video on your FYP of the people who are like reading fortunes, and they're like, take what resonates and leave what doesn't. If the math makes sense to you, great. Take what resonates and leave what doesn't. That's all that I beg. That's all that I beg of you. Anyway, as we were saying, this is for chloride. This is how we convert from milligrams per deciliter to millimoles per liter. Same thing for that. The 9. So blood is, or like the liquid portion of your blood, the water portion. So your blood is, that is a horrible drawing of a blood tube. If I have blood in my tube and I spin my tube down, I'm going to end up with a situation where I have a bunch of cells and I have my plasma or serum, depending on what kind of tube this was drawn in. Cells are going to equal roughly 45% of that tube, and plasma is going to equal roughly 55, I should say plasma or serum. It's going to equal roughly 55. This little sliver of white blood cells is going to be roughly 1%, if not less. Of the 55% of the plasma, of the serum, of the water component of your blood, the liquid component of your blood, plasma is roughly 92 to 93% water. For the sake of making the math easier, we round that to 90% water, because no one in lab likes to do math unless you're crazy like me. The 9 here is an adjustment factor to account for the fact that your serum is 90% water. That's the whole reason it's there. So the overall breakdown, one more time. This portion is to get the impact that sodium and chloride have on the osmolality. This portion is to convert your glucose concentration to the correct units so that the math is consistent across the board. This right here for your BUN is to make sure that your nitrogen is converted to the right units so the math is the same. And this right here is a correction factor to make sure that your math reflects the fact that serum is 90% water. There are some labs that straight up don't use this 9, like the correction factor, at all. We do, because again, the ASCP hates us. So let's go through a couple of case studies just to kind of get through what's going on here. Patient presents to the ER complaining of NV without D. So nausea and vomiting, no diarrhea. Fatigue, disorientation, muscle cramping, and abdominal discomfort. Thorough patient history reveals the patient is rushing a fraternity and was instructed to drink several jugs of water as part of his hazing. Physician orders a CMP with electrolytes. Using the results, calculate the patient's serum osmolality and interpret his results. So for serum osmolality, I'm just going to take my formula and I'm going to start plugging and chugging. So 1.86 times 135, which is what's here. You notice how this is already in millimoles per liter and this is in milligrams per deciliter. I don't have to convert my sodium because we never have to convert our sodium because you're never going to measure sodium in milligrams per deciliter. I don't think I've ever seen a single lab do that. Anyway, that's why we don't convert it, is because we don't have to, because it's already in the unit that we need it to be at the end. Plus glucose, which is 77 milligrams per deciliter. This is a measurement of concentration, so that's our concentration of glucose. So 77 over our correction factor to get the units correct, plus 9 over our correction factor for BUN plus 9. Let's do math. So 1.86 times 135, that's going to equal, I like to do stepwise math. I've noticed that a lot of the professors don't. So their rounding may end up being different than mine is if you like to do stepwise like I do. 251.1 plus 18, 4.28 roughly, plus 9 over 2.8, 3.21 plus 9. 251.1 plus 4.28 plus 3.21 plus 9. That's going to equal roughly 267.59 millimoles per liter. You may also see it written as milliosmoles per kilogram. Either way, doesn't matter. Our reference interval for serum, because this is our serum osmolality that we're doing, and this is the values from our serum. Our reference interval for serum osmolality is 275 to 295. 267.59 is below that reference range. So what does that mean? That means that he has decreased serum osmolality. Now, let's talk about why. So, this patient is rushing a fraternity, and he was instructed to drink several jugs of water as part of his hazing. This is based on a real story and a real case that I saw when I was working in the ER. Had to drink several jugs of water. The more water that he drank, the more that water diluted out the stuff that was in his blood, right? So osmolality is a measurement of how much stuff is in your blood. It's a measurement of how concentrated that stuff in your blood is. The more water you have without increasing the amount of stuff present in the water, the lower your osmolality is going to be because the stuff that's present in your blood is less concentrated, right? That's how it works. So, yeah, I don't think that there's anything else really to go over that. Basically, the dude drank too much water and diluted his own blood below normal. So you started seeing nausea, vomiting because there's too much water. Sometimes that can be your body is trying to get your osmolality back in check. So you start vomiting a lot to try and lose fluids. He hasn't had this long enough to start experiencing diarrhea because it was earlier in the day. Fatigue, when you have water intoxication, which is what this is called. It's called water intoxication. Water intoxication can disrupt the normal electrolyte levels within your body. a lot of the electrolyte levels that are in your body have to do with like muscle integrity, neuromuscular function, things like that. You're going to feel tired if you don't have enough electrolytes to keep your body moving. Disorientation, because a lot of the electrolytes are involved in like neural pathways and like neurogenic stuff. You might see a little bit disorientation. They might be a little bit confused because they don't have the right amount of electrolytes to make their body work. Muscle cramping, again, same thing. Neuromuscular function is impacted by too much water. Abdominal discomfort is quite literally just because there is too much water physically in his stomach and it is pushing on everything else, and he is like a pressurized water balloon. Yeah. Anyway, next question. A 9-year-old boy presents to his family physician for his yearly checkup. While at the appointment, the patient's mother jokes about how much water her son drinks, stating it's like it just runs right through him. Further questioning reveals that when the patient is unable to access water, he reports physical discomfort. The physician orders a CMP with electrolytes and a renal panel, so this is for our kidneys, and warns the patient's mother that the patient may need to perform a water deprivation test depending on results. Using the following information, calculate and interpret the patient's serum osmolality. This is a trick question, and I'll go through why this is a trick question after we answer it, but I just want you to know this is a case of drinking too much water. And this is an acute presentation, meaning the symptoms onset that day. This is something that has just very recently occurred. So all of the symptoms that we're seeing are new. They are not something that this patient has been dealing with for a long period of time. The symptom that we see is drinking too much water. But this appears to be something more chronic, not something acute. So we need to investigate a little bit more. Something else. The mom's phrasing of "it's like it just runs right through him" implies, and I was going to put this in here, and I forgot to, implies that the patient is urinating too much. The patient is losing water just as fast as he is taking it in, as fast as he is ingesting it. So when we look at this, we can't just say a patient is drinking too much water and jump to the conclusion that that's always going to result in a decreased osmolality. We have to investigate and make sure that they are not also losing too much water. So we're gaining a lot of water, but we're also seeming to be losing a lot of water. And further, there's another symptom that I'll get to after we get through this. He reports physical discomfort when he is not able to access water. So let's go ahead and real quick just go through the calculation steps. That's going to be 1.86 times 152 plus our glucose, which is 99 over 18, plus our BUN, which is 22 over 2.8 plus 9. So 1.86 times 152 is 282.72 plus 99 over 18, 5.5 plus 22 over 2.8, 7.86 plus 9, 282.72 plus 5.5 plus 7.86 plus 9. That is going to roughly equal 305.08 millimoles per liter. Okay. If our reference range is 275 to 295, 305.8 is really elevated. So, what's happening here? Like I said earlier, the patient is drinking a lot of water. His mom was saying that he drinks a lot of water. Problem is, he's urinating way too much. So not only he's getting a lot of water, he's losing more. He is drinking water to compensate for the fact that he's losing too much water. This is indicative of a condition known as diabetes insipidus. Diabetes insipidus is one of the big causes of increased osmolality. So if decreased osmolality, I'm going to go back to this other one for a second, equals too much water or not enough stuff, then an increased osmolality equals too much stuff or not enough water. Okay, so basically, if it's increased, you are too concentrated in your blood. So, diabetes insipidus, going back to what I was talking about a second ago, sorry, I did not plan this lecture out before I started doing it, I just started doing it. Diabetes insipidus is a condition where the body either does not produce ADH or does not respond to ADH. ADH is antidiuretic hormone. This is the don't pee hormone. Don't pee hormone. If you are not producing or not responding to the don't pee hormone, then your body sees pee. There's no hormone. This is the only instruction that the body sees is pee. So what happens is you're not producing or not responding to ADH. You can't not urinate. You can't not go to the restroom. And so then you start to have like hyperosmolarity. And so your brain triggers your body to be thirsty. And your brain is like, hey, please drink a lot of water. This ties into the RAS system, remember, from like renal stuff. RAS is supposed to cause the production of ADH as well. If it's not causing the production of ADH because you can't produce ADH, or if it's causing the production of ADH but the kidneys can't receive ADH, then this is broken. But at the very least, your RAS system can say, you're thirsty, go drink. So because you can't produce ADH, because you can't respond to ADH, whatever it is, you are peeing a lot. Your body compensates for that by getting thirsty and by drinking a lot. So that's why this patient's mother says that it just runs right through him. It's why he's drinking water all of the time. One of the follow-up tests that we do with those patients who we think may have diabetes insipidus is a water deprivation test, which is basically just they don't get access to water for like 2 to 8 hours, I believe. And we see if it causes them physical pain. It's kind of draconian in terms of testing methodologies. It's not like a laboratory test that we do. It's something that is done in the physician's office, kind of like a allergen challenge test. It's something that they handle, which is good because I wouldn't want to have to sit there with a 9-year-old crying because they are physically uncomfortable because they want water. Anyway, sorry, I'm rambling. The point here with this case study is that this patient is losing too much water even though they're drinking a lot of water. They're losing more than they're drinking, and it's causing their serum osmolality to elevate. We're going to go through a couple of other formulas that you need to know real quick with some tips. So, osmol gap. Osmol gap is basically how we determine like how right was our analyzer. So you take your osmolality, what the analyzer measured, and then what the analyzer calculated. So this is basically like the chemical stuff. This is the chemical measurement versus the calculated osmolality. This is like done through a different method. It's like seeing how, like, I think that this is done by nephelometry or by spectrophotometry. The point is, we don't look for like a specific analyte. We just look to see like how much stuff is there versus we take the specific analytes that we measured with specific tests and we calculate out the calculated osmolality and then we subtract the calculated osmolality from the measured osmolality. If that number is more than the reference interval, which is 15, that indicates that something is missing. Something is occluding the result. Something is interfering with the measurement. Because you have to remember, the formula for osmolality, if we look up here, let me erase these notes. If we look at the formula for osmolality, like I said earlier, we don't even account for chloride, right? Like, where's chloride? Where's glucose? Where's BUN? But there's other stuff that is also present in the serum that we don't include in this, right? What happened to, I don't know, potassium, right? What if, like, there's a lot of hemolysis and all of the stuff is exploding out of the cells and it's there in the serum and that we just don't expect it. So how would we know to compensate for it? What if there's a bunch of albumin present in the sample? What if the patient has multiple myeloma and they're producing a bunch of immunoglobulins that would be present in the serum that would be increasing the osmolality? The reason we calculate osmol gap is because osmolality makes a lot of assumptions that the patient has a lot of things that are not wrong with them. When we're calculating osmolality, we're assuming that they don't have a lot of hemolysis. We're assuming that they don't have a bunch of albumin floating around in solution. We're assuming that they're not dehydrated. We're assuming that they don't have multiple myeloma and have a bunch of immunoglobulins floating around in their system. We calculate the osmol gap specifically to like ensure we're ensuring that the calculation is correct, and we're ensuring that the analyzer is correct. If these two things are correlating, that's good. That's a good thing. If the measurement is significantly higher than the calculated osmolality, that means that there's a bunch of stuff floating around in the serum that formula doesn't account for that needs further investigation. We need to figure out why the osmol gap is so high because something is up. This is a physiological thing that, like, there are physiological reasons for why that reference interval, like for why it would be that elevated. But you do need to figure out what analyte specifically is causing the discrepancy between the measured and the calculated, is the point. Know how to calculate this. It's a plug and chug, so I don't think that we need to go into the math or do examples on it. Just know how to calculate it and know that the reference interval is that it should be less than 15 because these two things should be close together. For Henderson-Hasselbalch, some of y'all have said that she's not testing you over this. As far as I'm aware, you will not physically be able to calculate Henderson-Hasselbalch, the pH calculation, on your exam because you have 4 function calculators and those you cannot do logarithms with. That being said, it's still worth being able to recognize the formula because I know in the past questions on this exam have included like which of the following is the Henderson-Hasselbalch equation. So like you have to be able to like pick it out of a lineup essentially. Isoelectric point, this is another one that's a plug and chug, so I didn't see the point in like going through it. All that you need to know for isoelectric point is that that is when your amino acids, that's the context that we talk about this in, are in their Zwitter ion status, which is where they are amphoteric. It's where they're like at the balance point, isoelectrically speaking. So that's what the isoelectric point literally means. It's just, you'll get, like, we had exam questions over this, so I wouldn't be surprised if you also have them. You will get 2 pKa's All that you're doing is finding the average between those two pKa's. That's it. That's all that that formula is for. Yay! Congratulations, you survived, and you're now a lab math expert. And if you have questions over math, I love math, and I'm very excited and very happy to answer any questions that you may have, unless it's at 11 p.m. at night, I say as I'm recording this at 12:30 at night. So, congrats! Yay! Good luck on your exam.